So we're continuing with our review, and this time we want to discuss dot and cross products. And so far we've discussed the vector addition, scalar multiplication, and those are important operations on vectors, but there are two other ones that are very important. One is the dot product, which takes two vectors, v and w. Either both have to be in R2 or both have to be on R3, and it produces a scalar valued output v dot w. The cross product, which takes two vectors v and w, either both in they have to both be in R3, and then it produces an output of a vector v cross w. And so it's important to know a little bit of a geometry behind the dot and cross product, and not just the formula. It comes in handy in understanding of the concepts that relate to them. So definition of dot product is if we have two vectors, v equal to a1, b1, c1, and w equal to a2, b2, c2, or a sub 2, b sub 2, c sub 2, then the scalar v dot w is equal to the magnitude of v times magnitude of w times cosine of theta, where theta is the angle between v and w. Now if theta is acute, that means theta is between 0 and pi half, then v dot w is a positive value because cosine of acute angles is positive. If v and w are orthogonal to each other, that means theta is equal to pi half, then v dot w is going to be 0 because cosine of pi half is 0. If theta is obtuse, that's theta between pi half and pi, then v dot w is going to be less than 0. The angle between v and w can be computed. If you knew what v dot w is, you can use that to compute the angle by this formula: arc cosine of v dot w over the magnitude of v times magnitude of w. It turns out that using the formula v dot w equal to magnitude of v times magnitude of w times cosine of theta, you can show that there is an equivalent definition for v dot w, and that is if v dot w are in R2, then v and w are in R2, then the first coordinates multiplied together plus the second coordinates multiplied together is going to be the v dot w. That's if v is a1, b1, and w is a sub 2, b sub 2, then v dot w is a sub 1 times a sub 2 plus b sub 1 times b sub 2. And similarly, if v and w are in R3, then v dot w also is a1 dot a sub 1 times a sub 2, b sub 1 times b sub 2, c sub 1 times c sub 2. And so there is a beautiful little geometrical proof of that we want to see. So let's have V and W as shown there, and let theta be the angle between V and the angle made by V and x-axis, and theta 1 be that angle, and theta sub 2 be the angle made by W and x-axis. Now theta, which is the angle between V and W, is going to be theta 2 minus theta sub 1. Now what is the if you look at this area over here, you see that so V, and if I want to find A1 and A sub 1 and B sub 1, which are the coordinates of V, I just drop a vertical over here, but a vertical over here, which is A1, and vertical over there, that is B1, is just the magnitude of V times cosine of theta sub 1, and then B1 is magnitude of V times times sine theta 1. Similarly for W, if you basically A sub 2 is magnitude of W times cosine theta 2, B sub 2 is the magnitude of W times sine theta 2. Now if I look at the right hand side of the equation up there, right here, and I multiply A sub 1 times A sub 2 and B sub 1 times B sub 2 and add it together, we end up with the magnitude of V times magnitude of W times this cosine theta 1 cosine theta 2 plus sine theta 1 sine theta 2, and that is actually the magnitude of V times magnitude of W times cosine of theta 2 minus theta 1. With the description was that cosine of theta 2 minus theta 1 is just cosine theta, so we just proved that A sub 1 times A sub 2 plus B sub 1 times B sub 2 is equal to the dot product of V times W. So here's the usage, and not necessarily always, but this formula over here in this page, the formula that you use the coordinates to find the dot product, is the one that we normally use to actually find the actual value, the scalar number, the scalar that is the dot product. The other formula in the previous page, so the formula over here and in here, again, as we discussed, we can figure out information about the position that the two vectors are with respect to each other, and so this formula also comes in proofs and properties. The other one calculates the values for us. This one comes in for proofs and properties, basically, and we showed that the two of them are equivalent. iClicker question A. Which of the following expressions has meaning? The other four are nonsense. Option A dot B, vector A dot vector B dot vector C. Option B, vector A dot vector B plus vector c. Option C, vector A dot vector B times vector C. D, the magnitude of vector A dot B plus C, vector B plus C, vector C. E, the magnitude of A plus B dot vector C. Okay, I hope you paused and tried to find out the answer to this one. Let's see. When we're doing dot product, both things that you're multiplying together should be vectors. So over here you have A dot B, both of them are vector. That's good. The output of this product is going to be scalar. And so a scalar does not dot with C. It's scalar multiplication. So this one is nonsensical. Over here, A dot B, both of them are vectors, but plus C, this is a scalar. Scalars do not add up with vectors. This is nonsensical. A dot B is a scalar, and that part is defined, and then you multiply it by C. Oh, this is scalar multiplication, and that is fine. Let's check the rest of them also. We found the answer, but make sure that the rest are working correctly too. Here, magnitude of A is just a number, it's a scalar. It does not dot with another with addition of two vectors, that is a vector also. Over here, A plus B, magnitude of that is a scalar. It does not dot with C. So the answer is C. The cross product. The cross product of vector V and W in R3 is the vector V cross W equal to magnitude of V times magnitude of W times sine theta. This entire thing was a scalar multiplied by a vector and a unit vector, and so theta is the angle between V and W, and is the unit vector perpendicular to both V and W given by the right hand rule. That is, point your fingers from, this is V is the first angle, first vector, W is the second vector, and W is the second vector, and then if you put your all your fingers from V to W and stick your thumbs out, the thumb is in the direction of N. That's basically giving a thumbs up, going from V to W with all the fingers but thumbs, and then thumbs is up in the direction of N. In terms of basis for R3, how it works is that if you, this is the circular motion, and so you start from I, then J, then K, oh sorry, I, J, going from I, J, K, if you multiply I first, then J, then you get K. If you multiply J, then K, J, it's K, and you can put an arrow on top or not. I and J and K are always the unit vectors that make the base, and so j cross k is going to give you I, then k cross I is going to give you j. If you change the order of any of these, the other side becomes negative. So if you go, instead of I times j, if you go j cross I, then you get negative k. If you go k cross j, then it's negative I. And if you go I cross k, then it's negative j. Some properties of the cross product: if v and w are parallel, then sine of theta is going to be 0, so v cross w is going to be 0. If v cross w is perpendicular to v, and also it's perpendicular to w, so the cross product is perpendicular to both vectors that multiplied by cross product, and that's the reason is that the cross product is a vector in a direction that is perpendicular to the two vectors. If you multiply v cross w, if you change the order, it becomes minus w cross v. And then the other interesting part is that the magnitude of v cross w is the area of the parallelogram with sides v and w. So it's the magnitude of v cross w is the area of this parallelogram, basically. And why is that? Because just imagine the magnitude of v is this length, magnitude of w is this length, and if you multiply, let's say, the magnitude of v by sine of theta, you get this length, which is the height, and then you multiply height by the magnitude w, and you get the area of the parallelogram. If you want to calculate cross product of two vectors in R2, basically this is, let's say, for the purpose of finding an area of the parallelogram, you can actually imagine that R2 is a subset of R3, and then how does make the vectors work? That makes the vector, let's say, if a vector is v1 and v2, we can imagine it as v1, v2, and 0, because we're saying that it's the subset of the plane being a subset of R3, and the same way with w, which is w1 and w2 in R2. If we imagine R2 is just the plane xy plane in R3, then we can put a 0 for z and make another three-dimensional vector, and then we can cross product them. In that case, the v cross w is always a multiple of k, the standard basis for base member for R3. So let's do a little review of calculating cross products with of determinants, and then calculating the cross product with using the determinants. A determinant of a 2 by 2 matrix A, B, C, D is shown by this two lines around A, B, C, D. and then that would be A times D minus B times C. So A times D as in the diagonals minus B times C. And so what is the determinant of a 3 by 3 matrix? That actually uses is a recursive definition that we use, and we basically can expand the determinant of a 3 by 3 matrix. See that again, 2 lines over here means determinant over any row or any column, and it has a process attached to it. For the purpose of Calc 3, we're just going to discuss basically expanding on the first row over here. So how does this work? Expanding over the first row, you take the first entry in the first row, then you eliminate everything in the column and the row that contains that entry. So what is left is B sub 2, B sub 3, C sub 3, C sub 2, C sub 3. And you find the determinant of what is remaining and you multiply it by the entry. Now, so that's the first one. Then you subtract from, you take the second element of the row, a member of the row, and then you eliminate everything, every row and column that, the row and the column that contains A2. What is remaining is B1, C1, B3, C2, C3. And so you find the determinant of that and multiply by that element. You subtract. Subtraction here is very important. The other two are plus. This one is a negative. Now, what about the last one? The last one is the last entry over here, and you eliminate the elements in the row and column, and what is left is B1, B2, C1, and C2. You multiply it by, you find the determinant of that, and you multiply it by A3, which is that element. So basically you figured out the definition of determinant for a 2 by 2. Then you use that to find the definition of, you use that 3 times in the definition of the determinant of 3 by 3 matrix. So the beauty of all that is that now we can find, without telling you the proof of it, that the definition of the cross product is also equivalent. And again, this is how you calculate it, like as we did in dot product. The other formulas with the trig functions are more of understanding of the of how dot and cross product work, but the formulas with the coordinates are the ones that you compute the dot and cross product, most likely. Not necessarily always, but most likely. And so over here, the cross product of V cross W is equal to, put an ijk, and then the coordinates of V and coordinates of W, second and third row, and find the determinant of that. And through the expansions, you will have something multiplied by I, something multiplied by J, something multiplied by K, which makes it a vector in the 3 dimension. So what we computed was 2I plus 4J. So hopefully you paused and you found the values. Let's think about this. There are 3 points in here, and we want to find the orthogonal vector to vectors formed by the 3. The 3 vectors are, how many different ways we can find? We can find PQ, we can find QP, we can find PR, we can find RP, we can find QR and RQ. It really doesn't matter as long as you choose two of them that are not collinear or parallel to each other. And so now let's choose PQ and Q and PR, basically PQ and PR, and let's find it. PQ here, subtract -1 minus 3 minus 4, 0 minus 2 minus 2, 1 minus 1, 0, and then find PR, and PR is 1 minus 3, which is -2, and then it is -1 minus 2, which is -3, and 0 minus 1, which is -1. So you found two vectors there. Now the property of cross product is that the value of the output and the vector that is the output is perpendicular to the input. So cross the two of them together to get the perpendicular vector. So PQ cross PR. So crossing determinant of IJK, then the first vector, the order matters for dot product it didn't. And when you're basically, let's say expanding over IJK, when I have I, then I'm gonna eliminate everything else and calculate -2, 0, -1, -3, and -1. Then for the second row, so I eliminated that row and column. Now I have to have negative for the second one for J, -J. Then I have to eliminate basically the row and the column that J is at. So that elimination is this and here, and what is left is -4, 0, -2, and -1. Now K, for K it's plus K, and let's eliminate everything that is in K. So that's basically this row and column, and what is left is -4, -2, -2, and now let's calculate the first one over here. That's -2 times -1 minus 0 times -3. So the entire thing is +2 times I. The second one is negative times -4 minus 1 times -1 minus 0 times -2. So that is 4. So minus 4J, then -4 times -3, which is 12, minus -2 times -2, which is 4, and that is 8K. And so let's compare to the vectors that we have. So what was the vector we found? 2I plus minus 4J plus 8K, right? And now none of these are that. let me first of all write it. This is this 2 goes as the first component. What multiplies j goes the second component. What multiplies k goes at the third component. So that's the other way of writing it. And I look at all of these. None of them are that, but one of them is parallel to that. If a vector is parallel to that, that would still be perpendicular to both vectors. And which one is parallel to that? The one D is the one that is parallel to this vector, because it's 2 times the D is going to be this vector.